Hello everyone. Welcome to this full course video on machine learning algorithms. Machine learning algorithms are being commonly used in industries such as e-commerce, manufacturing and healthcare to build complex machine learning models. Our experienced instructors will help you understand the intuition behind these algorithms. You will start by understanding the basics of machine learning from a short animated video. Then, you will learn some of the top supervised learning algorithms such as linear regression, logistic regression, decision trees, support vector machines and k-nearest neighbors. Moving further, we will shift our focus on unsupervised learning algorithms such as k-means clustering and principal component analysis. Finally, we look at reinforcement learning and Q-learning algorithm. Now all these algorithms will be covered with extensive hands-on demonstrations in Python. So let's begin.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with their respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are two clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these two clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder, how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody's online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side. Keep watching this space for more interesting videos. Until then, happy learning.
Welcome to Linear Regression. My name is Richard Kirschner. I'm with Simplilearn. Let's look at an example of a common use for linear regression. Profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. What's in it for you? First, we'll have an introduction to machine learning, followed by machine learning algorithms. These will be specific to linear regression and where it fits into the larger model. Then we'll take a look at applications of linear regression, understanding linear regression, and multiple linear regression. Finally, we'll roll up our sleeves and do a little programming in use case profit estimation of companies. Let's go ahead and jump in. Let's start with our introduction to machine learning, along with some machine learning algorithms and where that fits in with linear regression. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that. We put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your C coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a colon -1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carries return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have x equals x colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case we do x train and y train because we're using the training data. X being the data in and Y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x_test. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have y_predict equals regressor.predict, x_test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m to the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the r² value, that's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the r² value. We're looking at the error. So, in the R2 score, we take our y_test versus our y_predict. Y_test is the actual values we're testing. That was the one that was given to us that we know are true. The y_predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if r² value of 0.91 or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
What is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between, and what is the employee's rating, okay? And ratings can be continuous, that is not an issue, but the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because looks like there will be a lot of errors. The root mean square error, if you remember for linear regression, would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers. and the others other than diagonals, the cells other than the diagonals should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0 and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and one has been predicted as number 8 and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks.
So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values, so which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9, and this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because they'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have x going in where we're going to train it, and we have to know the answer to train it with. And then we have x test where we're going to test that data. And we have to know in the end what the y was supposed to be. And that's where this train test split comes in that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on. And then we put in our yPredict in, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. Why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. So we have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So when we have all that data we're training, we can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes those decisions is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out how does a decision tree work. So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle. It's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there, and let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have them. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target, and let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here, and before I run it, I want to look at a couple things going on. So we have df species, and this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column, and here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the DF columns, and we know the first four of them, 0, 1, 2, 3, that'd be the first four, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first four. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this automatically treats this just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predictTestFeatures. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names, and we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this, and this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising, since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Last week, my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you can figure out that it was a strawberry. So let's take this model a step further, and why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the 2 groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have 2 groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in 2 lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the 2 classes. Here you can see there's a clear split between the 2 different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the 2. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have 2 sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a 2-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a 2-dimensional output. As you can see in this picture here, the 1D when transferred to a 2-dimensional makes it very easy to draw a line between the 2 data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a 2-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the 2 classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These 3 advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the 2 groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here in the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. And let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the np for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import and make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals SVM.SVC kernel equals linear, and I set C equal to 1, although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane, so we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y, and that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created two blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our two sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our makeBlobs returns a NumPy array. And this notation is great because what it means is the first part is the colon, means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dots, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using two colors, 0, 1, and that's why we get the nice blue and the two different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here. And I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed, right there on line 5. I'll go ahead and just delete that out of there, because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals plt.gca. Now right now we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is a very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these numpy commands mean with the line space and the mesh grid. We've taken xx, small xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together so it forms a nice grid. So if we were going to do this, say between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created and we've already trained. And we have a dot decision function, and we're going to put the XY in there. So here we have all this data. We're going to put that XY in there, that data, and we're going to reshape it. And you'll see that we have the XX.shape in here. This literally takes the XX, resets it up connected to the Y, and the Z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the Z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it. And we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data. And we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our two support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the two different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the two groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future, and you can see how easy they are to set up and look at in depth. Today we're going to cover the K nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning, and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this. so these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, is none. It doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column .mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replace that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the K-neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of ways to measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
What is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data, which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want 2 clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. There are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm, and then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering. hierarchical clustering, and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering, and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D, and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add B, C to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value, and that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of K, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster, with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned a value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we pick the centroids randomly, so they are not real centroids. So now what we have to do, we have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to CK and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. X1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick k cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to CK. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each x value from each c value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into k groups because we wanted to create k clusters, right? So we have k groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have k groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of k-means clustering. We will actually see some live demos in Python Notebook, using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in Scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. and this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does, and we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest, and accordingly we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but in the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001. We can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue, and this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this, the 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new, just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering. And we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering. And we use some sample data using blob to just execute the k-means clustering.
The principal component analysis, we're going to cover dimensionality reduction, principal component analysis, what is it, important PCA terminologies, and you'll see it abbreviated normally as PCA, principal component analysis, PCA properties, PCA example, and then we'll pull up some Python code in our Jupyter Notebook and have some hands-on demo on the PCA and how it's used. Dimensionality reduction. Dimensionality reduction refers to the technique that reduces the number of input variables in a data set. And so you can see on the table on the right shows the orders made at an automobile parts retailer. The retailer sells different automobile parts from different companies. And you can see we have company BPAX, Isomax, and they have the item, the tire, the axle, an order ID, a price number, and a quantity. In order to predict the future sales, we find out that using correlation analysis that we just need 3 attributes. Therefore, we have reduced the number of attributes from 5 to 3. And clearly we don't really care about the part number. I don't think the part number would have an effect on how many tires are bought. And even the store, who's buying them, probably does not have an effect on that. In this case, that's what they've actually done, is remove those. And we just have the item, the tire, the price, and the quantity. One of the things you should be taking away from this is, in the scheme of things, we are in the descriptive phase. We're describing the data, and we're pre-processing the data. What can we do to clean it up? Why dimensionality reduction? Well, number one, less dimensions for a given data set means less computation or training time. That can be really important if you're trying a number of different models and you're rerunning them over and over again. And even if you have 7 gigabytes of data, that can start taking days to go through all those different models. So this is huge. This is probably the hugest part as far as reducing our data set. Redundancy is removed after removing similar entries from the data set. Again, pre-processing, some of our models, like a neural network, if you put in 2 of the same data, it might give them a higher weight than they would if it was just one. So we want to get rid of that redundancy. It also increases the processing time if you have multiple data coming in. Space required to store the data is reduced. So if we're committing this into a big data pool, we might not send the company that bought it. Why would we want to store 2 whole extra columns when we add it into that pool of data? Makes the data easy for plotting in 2D and 3D plots. This is my favorite part. Very important. You're in your shareholder meeting. You want to be able to give them a really good, clear, and simplified version. You want to reduce it down to something people can take in. It helps to find out the most significant features and skip the rest, which also comes in post-scribing. Leads to better human interpretation. That kind of goes with number 4, where it makes data easy for plotting. You have a better interpretation when we're looking at it. Principal component analysis. So what is it? Principal component analysis is a technique for reducing the dimensionality of data sets, increasing interpretability, but at the same time minimizing information loss. So we take some very complex data set with lots of variables, we run it through the PCA, we reduce the variables. We end up with a reduced variable setup. This is very confusing to look at because if you look at the end result, we have the different colors all lined up. So what we're going to take a look at is, let's say we have a picture here. Let's say you are asked to take a picture of some toddlers and you are deciding which angle would be the best to take the picture from. So if we come up here and we look at this, we say, okay, this is one angle. We get the back of a lot of heads, not many faces. So we'll do it from here. We might get the one person up front smiling. A lot of the people in the class are missing, so we have a huge amount off to the right of blank space. Maybe from up here, again, we have the back of someone's head. And it turns out that the best angle to click the picture from might be this bottom left angle. You look at it and you say, hey, that makes sense. It's a good configuration of all the people in the picture. Now, when we're talking about data, it's not, you really can't do it by what you think is going to be the best. We need to have some kind of mathematical formula so it's consistent and so it makes sense in the back end. One of the projects I worked on many years ago had something similar to the iris. And if you've ever done the iris data set, it's probably one of the most common ones out there where they have the flower and they're measuring the stamen in the petals, and they have width and they have length of the petal. Instead of putting through the width and the length of the petal, we could just as easily do the width to length ratio. We can divide the width by the length and you get a single number where you had 2. That's the kind of idea that's going on into this in pre-processing and looking at what we can do to bring the data down. A very simplified example on my iris petal example. When we look at the similarity in PCA, we find the best picture or projection of the data points. And so when we look down at from one angle, we've drawn a line down there, we can see these data points based on, in this case, just 2 variables. Now keep in mind, we're usually talking about 36, 40 variables. Almost all of your business models usually have about 26 to 27 different variables they're looking at. Same thing with like a bank loan model. We're talking 26 to 36 different variables they're looking at that are going in. So what we want to do is we want to find the best view. In this case, we're just looking at the XY. We look down at it and we have our second idea, PC2. And again, we're looking at the XY, this time from a different direction. Here, for our ease, we can consider that we get 2 principal components, namely PC1 and PC2. Comparing both the principal components, we find the data points are sufficiently spaced in PC1. So if you look at what we got here, we have PC1. You can see along the line how the data points are spaced versus the spacing in PC2. And that's what they're coming up with. What is going to give us the best look for these data points when we combine them? And we're looking at them from just a single angle. Whereas in PC2, they are less spaced, which makes the observation and further calculations much more difficult. Therefore, we accept the PC1 and not the PC2 as the data points are more spaced. Now, obviously, the back-end calculations are a little bit more complicated when we get into the math of how they decide what is more valuable. This gives you an idea, though, that when we're talking about this, we're talking about the perspective, which would help in understanding how PCA analysis works. What we want to go ahead and do is dive into the important terminologies under PCA. And important terminologies are views, the perspective through which data points are observed. And so you'll hear that if someone's talking about a PCA presentation and they're not taking the time to reduce it to something that the average person, shareholders, can understand, you might hear them refer to it as the different views. What view are we taking? Dimension, number of columns in a data set are called the dimensions of that data set. And we talked about, you'll hear features, dimensions. I was talking about features. There's usually When you're running a business, you're talking 25, 26, 27 different features minimal. And then you have the principal component, new variables that are constructed as linear combinations or mixtures of the initial variables. Principal component is very important. It's a combination. If you remember my flower example, it would be the width over the length of the petal as opposed to putting both width and length in. You just put in the ratio instead, which is a single number versus two separate numbers. Projections. The perpendicular distance between the principal component and the data points. And that goes to that line we had earlier. It's that right angle line of where how all those points fall onto the line. Important properties. Important properties. Number of principal components is always less than or equal to the number of attributes. That just makes common sense. You're not going to do 10 principal properties with only 3 features. You're trying to reduce them, so it's just kind of goofy, but it is important to remember that. People will throw weird code out there and just randomly do stuff instead of really thinking it through. Principal components are orthogonal. And this is what we're talking about, that right angle from the line. When we do PC1, we're looking at how those points fall on to that line. Same thing with PC2. And we want to make sure that PC1 does not equal PC2. We don't want to have the same 2 principal points when we do 2 points. The priority of principal components decreases as their numbers increase. This is important to understand. If you're going to create one principal component, everything is summarized into that one component. As we go to 2 components, the priority, how much it holds value, decreases as we go down. So if you have 5 different points, each one of those points is going to have less value than just the one point, which has everything summarized in it. How PCA works. I said there was more in the back end when we talk about the math. This is what we're talking about, is how does it actually work. So now we have understanding that you're looking at a perspective. Now we want to see how that math side works. PCA performs the following operations in order to evaluate the principal components for a given data set. First, we start with the standardization. Then we have a covariance matrix computation. And we use that to generate our igene vectors and igene values, which is the feature vector. And if you remember, the igene vector is like a translation if we're moving the data from x equals 1 to x equals 2 or whatever, altering it, and the igene value is the final value that we generate. When we talk about standardization, the main aim of this step is to standardize the range of the attributes so that each one of them lie within similar boundaries. This process involves removal of the mean from the variable values and scaling the data with respect to the standard deviation. And you can see here we have z equals the variable values minus the mean over the standard deviation. The covariance matrix computation. Covariance matrix is used to express the correlation between any 2 or more attributes in multi-dimensional data set. The covariance matrix has the entries as the variance and the covariance of the attribute values. The variance is denoted by var and the covariance is denoted by cov. On the right, we can see the covariance matrix for 2 attributes and their values. When we do a hands-on look at the code, we'll do a display of this so you can see what we're talking about and what that looks like. For now, you can just notice that this is a matrix that we're generating with the variance and then the covariance of x to y. On the right side, we can see the covariance table for more than 2 attributes in a multi-dimensional data set. This is what I was talking about. We usually are looking at not just 1 feature or 2 features. We're usually looking at 25, 30 features going on. And so if we do a setup like this, we should see all those different features as the different variables. Covariance matrix tells us how the 2 or more variables are related. Positive covariance indicate that the value of one variable is directly proportional to the other variable. Negative covariance indicate that the value of one variable is inversely proportional to the other variable. That is always important to note whenever we're doing any of these matrices, that we're going to be looking at that positive and negative, whether it's inverted or not. And then we have the eigene values and the eigene vectors. Eigene values and eigene vectors are the mathematical value that are extracted from the covariance table. They are responsible for the generation of a new set of variables from the old set of variables, which further lead to the construction of the principal components. Eigene vectors do not change directions after linear transformation. Eigene values are the scalars or the magnitude of the eigene vectors. And again, this is just transforming that data. So we're going to change the vector b to the b prime as denoted on the chart. And so when we have like multiple variables, how do we calculate that new variable? And then we have feature vectors. Feature vectors is simply a matrix that has eigene vectors of the components that we decide to keep as the columns. Here we decide whether we must keep or discard the less significant principal components that we have generated in the above steps. This becomes really important as we start looking at the back end of this, and we'll do this in the demo, but one of the more important steps to understand. And so we have the PCA example. Consider matrix X with n rows or observations and k columns or variables. Now for this matrix, we would construct a variable space with as many dimensions as the variable. But for our simplicity, let's consider this 3 dimensions for now. Now each observation, row of the matrix X, is placed in the k-dimensional variable space, such that the rows in the data table form a swarm of points in this space. Now we find the mean of all the observations and then place it along the data points on the plot. The first principal component is a line that best accounts for the shape of the point swarm. It represents the maximal variance direction in the data. Each observation may be projected onto this line in order to get a coordinate value along the PC1. This value is known as a score. Usually only one principal component is insufficient to model the systematic variation for a data set. Thus, a second principal axis is created. The second principal component is oriented such that it reflects the second largest source of variation in the data. While being orthogonal to PC1, PC2 also passes through the average point. Let's go ahead and pull this up and just see what that means inside our Python scripting. I'm going to use the Anaconda Navigator, and I will be in Python 3.6 for this example. I believe there's even like a 3.9 out. I tend to stay in 3.6 because a lot of the models I use, especially with the neural networks, are stable in 3.6. And then we open up our Jupyter. I'm in Chrome, and we go ahead and create a new Python 3. And for ease of use, our team in the back was nice enough to put this together for me. And we'll go ahead and start with the libraries. The first thing I like to do whenever I'm looking at any new setup, well, you know what, let's do the libraries first. We're going to do our basic libraries, which is matplotlib library, the PLT from the matplotlib library, pandas, our data frame, PD, numpy, our numbers array, np, seaborn for graphing, SNS, that goes with the plot that actually sits on matplotlib library, so the seaborn sits on there. And then we have our ampersand, because we're in Jupyter Notebook, matplotlib library inline. The newer version actually doesn't require that, but I put it in there anyway, just because I'm so used to it. And then we want to go ahead and take a look at the data. And in this case, we're going to pull in, certainly you can have lots of fun with different data, but we're going to use the cancer data set. And one of the reasons the cancer data set is it has like 36, 35 different features. So it's kind of fun to use that as our base for this. And we'll go ahead and run this and look at our keys. And the first thing we notice in our keys for the cancer data set is we have our data, we have our target, our frame, target names, description, feature names, and file name. So what we're looking for in all this is, well, let's take a look at the description. Let's go in here and pull up the description on here. I'm not going to spend a huge amount of time on the description because we don't want to get into a medical domain. We want to focus on our PCA setup. What's important is you start looking at what the different attributes are, what they mean. If you were in the medical field, you'd want to note all these different things, what they're measuring, where it's coming from. You can actually see the actual different measurements they're taking. No missing attributes. We page all the way to the bottom. And you're going to have your data, in this case our target. And if you dig deep enough to the target, let's actually do this. Let's go ahead and print target names. Real quick here, I always like to just take a look and see what's on the other end of this. Target names. Run that. And so the target name is it malignant or is it benign? So in other words, is this dangerous growth or is it something we don't have to worry about? That's the bottom line with the cancer in this case. And then we can go ahead and load our data. And you know what, let me go up just a notch here for easy of reading. It's hard to get that just right. I guess I'll have to do. So let's go ahead and look at our data. We're going to use our pandas, and we're going to go ahead and do our data frame. It's going to equal cancer data. Columns equals cancer, feature equals feature names. So remember up here, we already loaded the names up of the features in there. What is going to come out of this? Let me just see if I can get to that. It's at the top of target names. That's just this list of names here in the setup. And we can go ahead and run this code, and it'll print the head. And you can see here we have the mean radius, the mean texture, mean perimeter. I don't know about you, this is a wonderful data set if you're playing with it, because like most of the data that comes in, half the time we don't even know what we're looking at. We're just handed a bunch of stuff as a data scientist going, what the heck is this? And so this is a good place to start because this has a number of different features in there and we have no idea what these features mean or where they come from. We want to just look at the data and figure that out. And now we actually are getting into the PCA side of it. As we've noticed before, it is difficult to visualize high-dimensional data. We can use PCA to find the first two principal components and visualize the data, this new two-dimensional space, with a single scatter plot. Before we do this, we need to go ahead and scale our data. Now, I haven't run this to see if you really have to scale the data on this, but as just a general runtime, I almost do that as the first step of any modeling, even if it's pre-modeling as we're doing here. In neural networks, that is so important. With PCA visualization, it's already going to scale it when we do the means and deviation inside the PCA. But just in case, it's always good to scale it. And then we're going to take our PCA with the scikit-learn uses very similar process to other pre-processing functions that come with scikit-learn. We instantiate a PCA object, find the principal components using the fit method, then apply the rotation and dimensionality reduction by calling transform. We can also specify how many components we want to keep when creating the PCA object. And so the code for this, oops, getting a little bit ahead. Let me go ahead and run this code. So the code for this is from sklearn decomposition import PCA. PCA equals PCA and components equals 2. And that's really important to note that because we're only going to want to look at 2 components. I would never go over 4 components, especially if you're going to demo this with somebody else. If you're showing this to the shareholders, the whole idea is to reduce it to something people can see. And then the PCA fit, we're going to is going to take the scaled data that we generated up here, and then you can see we've created our PCA model with in components equals 2. Now, whenever I use a new tool, I like to go in there and actually see what I'm using. So let's go to the scikit webpage for the PCA. And you can see in here, here's our call statement. It describes what all the different setups you have on there. Probably the biggest one to look at would be, well, the biggest one is your components. How many components do you want? which you have to put in there pretty much. And then you also might look at the SVD solver. It's on auto right now, but you can override that and do different things with it. It does a pretty good job as it is. And if we go down, all the way down to, here we go, to our methods, if you notice we have fit and we have fit transform. Nowhere in here is predict, because this is not used for prediction. It's used to look at the data. Again, we're in the describe setup. We're fitting the data. We're taking a look at it. We've already looked at our minimum maximum. We've already looked at what's in each quarter. We've done a full description of the data. This is part of describing the data. That's the biggest thing I take away when I come zooming in here. And of course, they have examples of it down here if you forget. And the biggest one, of course, is the number of components. And then, the rest you can play with. The actual solver, whether you're doing a full or randomized, there's different things. It does pretty good on the auto. And now we can transform this data to its first two principal components. And so we have our XPCA. We're going to set that equal to PCA transform scaled data. So there we go. There's our first transformation. And let's just go ahead and print the scaled data shape and the XPCA data shape. And the reason we want to do this is just to show us what's going on here. We've taken 30 features. I think I said 36 or something like that, but it's 30. And we've compressed it down to 2 features. And we decided we wanted 2 features, and that's where this comes from. We still have 569 data sets. Data rows, not data sets. We still have 569 rows of data, but instead of computing 30 features, we're now only doing our model on 2 features. So let's go ahead and plot these and take a look and see what's going on. And we're just going to use our PLT figure. We're going to set the figure size on here. Here's our scatter plot, XPCA, X underscore PCA of 1. These are our 2 different perceptions we're using. And then you'll see right here, C for color, cancer equals target. And so remember, we have 0, we have 1. And if I remember correctly, 0 was malignant, 1 was benign. So everything in the 0 column is going to be 1 color, and the other color is going to be 1. And then we're going to use the plasma map, just kind of telling you what color it is. Add some labels, first principal component, second principal component. And we'll go ahead and run this. And you can see here, instead of having a chart, one of those heat maps with 30 different columns in it, we can look at this and say, hey, this one actually did a pretty good job of separating the data. And a couple things when I'm looking at this that I notice is, first, we have a very clear area where it's clumped together, where it's going to be benign. And we have a huge area, it's still clumped together, more spread out, where it's going to be malignant. Or I think I had that backwards. And then in the middle, because we're dealing with something, in this particular case, cancer, we would try to separate, I would be exploring how to separate this middle group out. In other words, there's an area where everything overlaps, and we're not going to have a clear result on it. Just because those are the people you'd want to go in there and have extra tests, or treat it differently, versus going in and saying just cutting into the cancer so that the body absorbs it and it dissipates, versus actively going in there, removing it, testing it, going through chemo and all the different things. That's a big difference, as far as what's going to happen here. And that middle line where they overlap is going to be huge. That's domain specific. Going back to the data, we can see here, clearly by using these 2 components, we can easily separate these 2 classes. So the next step is, what does that mean? Interpreting the components. Unfortunately, with this great power of dimensionality reduction comes the cost of not being able to easily understand what these components represent. I don't know what principal component 1 represents, or second principal. The components correspond to combinations of original features. The components themselves are stored as an attribute of the filtered PCA object. And so when we look at that, we can go ahead and look at the PCA components. This is in our model we built. We've trained it. We can run that, and you can see here's the actual components. It's the two components each have their own array. And within the array, you can see what the scores they're using. And these actually give weight to what features are doing what. So in this NumPy matrix array, each row represents a principal component, and each column relates back to the original features. What's really neat about this is we can now go in reverse and drop this onto a heat map and start seeing what this means. And so let me go ahead and just put this down. Oops, I already got it down here. We'll go ahead and put this in here. We're going to use our dfcomp data frame, and we do our PCA components. And I want you to notice how easy this is. We're going to set our columns equal to cancer feature names. That just makes it really easy. And we're dumping it into a data frame. What's neat about a data frame is when we get to Seaborn, it will pull that data frame apart and set it up for us the way we want. And so we're just going to do the Seaborn heat map of our data frame composition, and we'll use the plasma coloring. And it creates a nice little color graph here. You can see we have the mean radius and all the different features along the bottom. On the right, we have a scale, so we can see we have the dark colors all the way to the really light colors, which are what's really shining there. This is like the primary stuff we want to look at. So this heat map and the color bar basically represent the correlation between the various features and the principal component itself. So, very powerful map to look at, and then you can go in here, and we might notice that the mean radius, look how on the bottom of the map it is on some of this. So you have some interesting correlations here that change the variations on that and what means what. This is more when you get to PostScribe, you can also use this to try to guess as what these things mean and what you want to change to get a better result.
We're going to cover reinforcement learning today. And what's in it for you? We'll start with why reinforcement learning. We'll look at what is reinforcement learning. We'll see what the different kinds of learning strategies are that are being used today in computer models under supervised versus unsupervised versus reinforcement. We'll cover important terms specific to reinforcement learning. We'll talk about Markov's decision process, and we'll take a look at a reinforcement learning example. Well, we'll teach a tic-tac-toe how to play. Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. You can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important, as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is. How it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors. Used to solve reward-based problems. No predefined data is used. No supervision. Follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options, and we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that. And it goes, oh, this is also reward based. And so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, that you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward. A going to C and D would generate a different reward. Or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page. And I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array. And then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2 is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, the same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, is it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3 just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. We can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, it's going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game or even learn something that isn't a game is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where you yourself get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. this is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state, this is class player, and when we say class player, we're not talking about a human player, we're talking about just the computer players. And this is kind of interesting. So remember I told you depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it. As you try different moves, it gets to the end, the first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. This is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. I probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here, let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the self state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have our self setup on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available. you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here. And feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces. And the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go, and it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here, and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just 1 round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. And you can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that, I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time, instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3 by 3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. So you pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
A quick recap. So we're going to go back and do a reinforcement learning recap. And you'll remember we have our agent, our action, our environment, and our reward, and the state. And so reinforcement learning is a branch of machine learning that trains a model to come to an optimum solution for a problem by taking decisions by itself. So we look at it, we analyze the data, make decisions, solve problems. It consists of an environment which an agent will interact with to learn to reach a goal or perform an action. And you can see here we have the dog, and the action equals fetching. And the first thing you're going to notice here, and I'll talk a little bit more about this, is that our action is kind of a singularity. The action isn't a regression type model where we're looking at float numbers, or we're trying to predict something, or doing a reinforcement learning where we're trying to guess the value of the stock market, where you have 5.33, $5.33. This is a little bit different, and you'll see why Q-learning is so powerful, but also where it falls short. The agent is also given a reward if the action performed by it is bringing it closer to the goal, is leading to the goal. This is done to train the model in the right direction. You have a reward of hopefully a doggy cookie, and action equals fetching. So it gets a reward, it gets to go fetch the ball. Reinforcement learning can be divided based on whether the machine uses a model to learn or learns by itself. So reinforcement learning, it's model-based, learn the model, given model. And you can think of neural networks, I think, are the most common right now used for reinforcement learning. There certainly are a lot of other options out there. But you have this black box, and you go back and you send the error back up, and it trains it based on how much of an error. The error could be computed based on maybe a maximum reward subtraction or something like that. So the closer you get to the maximum reward, the better. And so we talk about a model free. You have your policy optimization and your Q-learning. And this is kind of the cool thing about Q-learning, is it's very powerful on certain things, making it very quick and easy to do a reinforcement learning. So what is Q-learning? Q-learning is reinforcement learning policy which will fill the next best action given a current state. It chooses this action at random and aims to maximize the reward. And so you can see here's our standard reinforcement learning graph. By now, if you're doing any reinforcement learning, you should be familiar with this, where you have your agent takes an action, the action affects the environment, and then the environment sends back the reward or the feedback, and the state, it's the new state the agent's in. Where is it at on the chessboard? Where is it at in the video game? If your robot's out there picking trash up off the side of the road, where is it at on the road? Consider an ad recommendation system. Usually when you look up a product online, you get ads which will suggest the same product over and over again. Using Q learning, we can make an ad recommendation system which will suggest related products to our previous purchase. The reward will be if user clicks on the suggested product. And again, you can see you might have a lot of products on your web advertisement or your pages, but it's still not a float number. It's still a set number. And that's something to be aware of when you're using Q learning. And you can see here that if you have 100 people clicking on ads and you click on one of the ads, it might go in there and say, okay, this person clicked on this ad. What is the best set of ads based on clicking on this ad or these two ads afterwards based on where they are browsing? So let's go ahead and take a look at some important terms when we talk about Q learning. We have states. The state S represents the current position of an agent in an environment. The action A is the step taken by the agent when it is a particular state. Rewards. For every action, the agent will get a positive or negative reward. And again, when we talk about states, we're usually not, when you're using a Q table, you're not usually talking about float variables. You're talking about true, false. And we'll take a closer look at that in a second. And episodes, when an agent ends up in a terminating state and can't take a new action. This might be if you're playing a video game, your character stepped in and is now dead or whatever. Q values used to determine how good an action A taken at a particular state S is Q A of S. And temporal difference, a formula used to find the Q value by using the value of the current state and action and previous state and action. And there's Bellman's equation, which basically is the equation that kind of covers what we just looked at in all those different terms. The Bellman equation is used to determine the values of a particular state and deduce how good it is to be in take that state. The optimal state will give us the highest optimal value. Factor influencing Q values, the current state and action, that's your SA, so your current state and your action. Then you have your previous state and action, which is your S, I guess prime, I'm not sure how they reference that, S prime, A prime. So this is what happened before. Then you have a reward for action, so you have your R reward, and you have your maximum expected future reward. And you can see there's also a learning rate put in there and a discount rate. So when we're looking at these, just like any other model, we don't want to have an absolute final value on here. We don't want it to, if you do absolute values instead of taking smaller steps, you don't really have that approach to the solution. You just have a jump, and then pretty soon if you jump one solution out, that's what's going to be the new solution, whichever one jumps up really high first. Kind of ruining the whole idea of doing a random selection. I'll go into the random selection in just a second. Steps in Q learning. Step 1. Create an initial Q table with all values initialized to 0. Again, we're looking at 0, 1. So here's our action. We start, we're in idle, we took a wrong action, we took a correct action, and end. And then we have our actions, fetching, sitting, and running. And of course, we're just using the dog example. And choose an action and perform it. Update values in the table. And of course, when we're choosing an action, we're going to kind of do something random and just randomly pick one. So you start out and you sit, and you have then depending on that action you took, you can now update the value for sitting after you start, from start to sitting. Get the value of the reward and calculate the value Q value using the Bellman equation. And so now we attach a reward to sitting. And when we attach all those rewards, we continue the same until the table is filled with or an episode ends. And I mentioned I was going to come back to the random side of this, and there's a few different formulas I use for the random setup to pick it. I usually let whatever queue model I'm using do their standard one, because someone's usually gone in and done the math for the optimal spread. But you can look at this. If I have running has a reward of 10, sitting has a reward of 7, fetching has a reward of 5, just kind of without doing like a means, using the bell curve for the means value, and like I said, there's some math you can put in there to pick so that you're more like, so that running has even a higher chance. But even if you were just going to do an average on this, you could do an average, a random number by adding them all together. So you get 10 plus 7 plus 5 is 22. You could do 0 to 22, or 0 to 21, but 1 to 22. 1 to 5 would be fetching, and so forth, the last 10. So you can just look at this as what percentage are you going to go for that particular option. And then that gets your random setup in there, and then as you slowly increment these up, you see that if you're idle, where's one? Here we go. Sitting at the end, if you're at the end of wherever you're at, sitting gets a reward of 1. Where's a good one on here? Oh, wrong action. Running for a wrong action gets almost no reward. So that becomes very, very less likely to happen, but it still might happen. It still might have a percentage of coming up. And that's where the random programming and Q learning comes in. The below table gives us an idea of how many times an action has been taken and how positively correct action or negatively wrong action it is going to affect the next state. So let's go ahead and dive in and pull up a little piece of code and see what this looks like in Python. In this demo, we'll use Q-learning to find the shortest path between two given points.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
If you've seen my videos before, I like to do it in the Anaconda Jupyter Notebook setup, just because it's really easy to see and it's a nice demo. And so here's my Anaconda. This one I'm actually using Python 3.6 environment that I set up in here. And we'll go ahead and launch the Jupyter Notebook on this. And once we're in our Jupyter Notebook, which has the kernel loaded with Python 3, we'll go ahead and create a new Python 3 folder in here. And we'll call this Q Learning. And to start this demo, let's go ahead and import our NumPy array. We'll just run that so it's imported. And like a lot of these model programs, when you're building them, you spend a lot of time putting it all together, and then you end up with this really short answer at the end. And we'll take a look at that as we come into it. So we go ahead and start with our location to state. So we have L1, L2. These are our 9 locations, 1 to 9. And then, of course, the state is going to be 0, 1, 2, 3, 4. It's just a mapping of our location to an integer on there. And then we have our actions. Our actions are simply moving from one location to another. So I can go to location 0, I can go to location 1, 2, 3, 4, 5, 6, 7, 8. So these are my actions I can choose. These are the locations of our state. And if you remember earlier, I mentioned that the limitation is that you don't want to put in a continually growing table, because you can actually create a dynamic queue table where you continually add in new values as they arise. Because if you have float values, it just becomes infinite, and then your memory in your computer is gone, or it's not going to work. At the same time, you might think, well, that kind of really limits the queue learning setup. But there are ways to use it in conjunction with other systems. And so you might look at, well, I've been doing some work in stock. And one of the questions that comes out is to buy or sell the stock. And the state coming in might be, you might take and create what we call buckets, where anything that you predict is going to return more than a certain amount of money the error for that stock that you've had in the past. You put those in buckets, and suddenly as you start creating these buckets, you realize you do have a limited amount of information coming in. You no longer have a float number. You now have bucket 1, 2, 3, and 4. And then you can take those buckets, put them through a Q learning table, and come up with the best action. Which stock should I buy? It's like gambling. Stock is pretty much gambling if you're doing day trading. You're not doing long-term investments. And so you can start looking at it like that. A lot of the current feeds say that the best algorithms used for day traders, where you're doing it on your own, is really to ask the question, do I want to trade the stock? Yes or no? And now you have it in a Q learning table, and now you can take it to that next level, and you can see where that can be a really powerful tool at the end of doing a basic linear regression model or something. What is the best investment? And you start getting the best reward on there. So if we're going to have rewards, these rewards we just create. It says if you're this should match our Q table, because it's going to be you have your state and you have your action across the top, if you remember from the dog. And so we have whatever state we're in going down, and then the next action and what the reward is for it. And of course, if you were actually doing something more connected, your reward would be based on the actual environment it's in. And then we want to go ahead and create a state to location so we can map the indexes. So just like we defined our rewards, we're going to go ahead and do state to location. And you can see here it's a dictionary setup for location state and location to state with items. And we also need to define what we want for learning rates. You remember we had our two different rates as far as like learning from the past and learning from the current. So we'll go ahead and set those to 0.75 and the alpha set to 0.9. And we'll see that when we do the formula. And of course, any of this code, send a note to our Simplilearn team. They'll get you a copy of this code on here. And let's go ahead and pull. There we go. Well, the next two sections. Since we're going to keep it short and sweet. Here we go. So let's go ahead and create our agent. So our agent is going to have our initialization where we send it all the information. We'll define our self gamma equals gamma. We could have just set the gamma rate down here instead of submitting it. It's kind of nice to keep them separate because you can play with these numbers. And our self alpha. Then we have our location state. We'll set that in here. We have our choice of actions. We're going to go ahead and just embed the rewards right into the agent. So obviously this would be coming from somewhere else instead of from self-generated. And then a self state to location equals our state to location dictionary. And we go ahead and create a Q learning table. And I went ahead and just set the Q learning table up to 0 to 0, what the setup is, location to state, how many of them are there. And this just creates an array of 0 to 0 setup on there. And then the big part is the training. We have our rewards new equals a copy of self.rewards. Ending state equals the self location state in location. So this is whatever we end up at. Rewards new equals ending state plus ending state equals 999. Just kind of goes to a dead end. And we start going through iterations. And we'll go ahead, let's do this. So this, we're going to come back and we're going to call it on here. Let me just erase that. Switch it to an arrow. There we go. So what we're doing is we're going to send in here to train it. We're going to say, hey, I want to iterate through this 1,000 times and see what happens. Now this part would actually be, instead of iterating, you might have your external environment and they're going back and forth and you iterate through outside of here. But just for ease of use, our agent's going to come in here and iterate through this. Sometimes I'll put this iteration in here and I'll have it call the environment and say, hey, this is what I did, what's the next state? And the environment does its thing right in here as I iterate through it. And then we want to go ahead and pick a random state to start with. That's what's going on here. You have to start somewhere. And then you have your playable actions. We're going to start with just an empty thing for playable actions, and we'll fill that up. So that's what choices I have. And so we're going to iterate through the rewards matrix to get the states, directly reachable from the randomly chosen current state. Assign those states to a list named playable actions. And so you can see here we have range 9. I usually use length of whatever I'm looking at, which is our locations or states as they are. We have a reward, so we want to look at the rewards. The new reward is in our chart here of rewards underscore new current state plus J. J being what is the next state we want to try. And so we go ahead and do our playable actions and we append J. And so what we're doing is we're randomly trying different things in here to see what's going to generate a better reward. And then of course we go ahead and choose our next state. So we have our random choice playable actions. And if you remember, I mentioned on this, let me just go ahead and, let's do a free form. When we were talking about the next state, this right here just does a random selection. Instead of a random selection, you might do something where whatever the best selection is, which might be option 3 here, and then so you can see that it might use a bell curve, and then option 2 over here might have a bell curve like this. Oops. And we start looking at these averages and these spreads, or we can just add them all together and pick the one that kind of goes in all of those. So those are some of the options we have in here. We just go with a random choice. That's usually where you start, play with it. And then we have our reward section down here. And so we want to go ahead and find, well in this case, the temporal difference. So you have your rewards new plus the self gamma, and this is the formula we were looking at. This is Bellman's equation here. So we have our current value, our learning rate, our discount rate involved in there, the reward system coming in for that, and we can add it all together. This is of course our maximum expected future setup in here. So this is all of our Bellman's equation that we're looking at here. And then we come up in here and we update our Q table. That's all this is on this one. And that's right here. We have self Q, current state, next state, and we add in our alpha because we don't want to train all of it at once in case there's slight differentials coming in there. We want to slowly approach the answer. And then we have our route equals the start location, and next location equals start location. So we're just incrementing. We took a step forward. And then finally, remember I was telling you how we're going to do all this and just have some simple thing at the end where it just generates a simple path. We're going to go ahead and get the optimal route. We want to find the best route in here. And so we've created a definition for the optimal route down here. Just scroll down for that. And we get the optimal route. We go ahead and put the information in, including the Q table, self, start location, end location, next location, route, Q. And it says while next location is not equal to end location, so while we can still go, our start location equals self location to state start location. So we already have our best value for the start location. The next state looks at the Q table and says, hey, what's the next one with the best value? And then the next location, we go ahead and pull that in and we just append it. That's what's going on down here. And then our start location equals the next location. And we just go through all the steps. And we'll go ahead and run this. And now that we have our Q table, our Q agent loaded, we're going to go ahead and take our Q agent, load them up with our alpha, gamma that we set up above, along with the location step, action, reward, state to location. And our goal is to plot a course between L9 and L1. And we're going to go through 1,000 iterations on here. And so when I run that, it runs pretty quick. Why is this so fast? If you've been running neural networks and you've been doing all these other models, you sit here and wait a long time. Well, we're a very small amount of data. These are all integers. These aren't float values. The math is not heavy on the processing end, and this is where Q tables are so powerful. If you have a small amount of information coming in, you very quickly get an answer off of this, even though we went through it 1,000 times to train it. And you'll see here we have L9, 8, 5, 2, and 1, and that's based on our reward table we had set up on there. And this is the shortest path going between these different setups in here. And if you remember on our reward table, you can see that if you start here, you can go to here. There's places you can't go. That's how this reward table was set up. So I can only go to certain places. So kind of a little maze set up in there. And you can play with it. This is really fun setup to play with. And you can see how you can take this whole code and you can, like I was saying earlier, you can embed it into another setup and model and predictions where you put things into buckets and you're trying to guess the best investment, the best course of action. Long as you can take that course of action and reduce it down to a yes, no. Or if you're using text, you can use a one-hot encoder, which word is next. There's all kinds of things you can do with a Q table, depending on just how much information you're putting in there. So that wraps up our demo. In this demo, we've found the shortest distance between two paths based on whatever rules or state rewards we have to get from point A to point B and what available actions there are.
And that brings us to the end of this video on machine learning algorithms. I hope you liked it. If you have any questions, then please put them in the comment section below. We'll be happy to answer them. Thank you for watching and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.